So welcome everyone to our, for me, late night, for some of you morning and some of you afternoon, I guess, practitioner track. We have two speakers today from Google on talking about a consolidated framework for forecast generation and evaluation. I'm sure many of you know them already, so we're expecting an exciting presentation. And I don't want to take more of your time, so please start.
Great. So great to be here. Thanks for having us. Really, I think this virtual ISF so far has been a great success. Of course, I wish we were all in person, but it's great to be here participating virtually and see folks from around the world and all the different time zones. Casey and I are going to be talking about a consolidated framework for forecast generation and evaluation. This is work that we've been putting together at Google over, actually over many years, kind of compiling pieces together, and we now have some really nice progress that I want to share and kind of put out to the community a little bit. We'll jump into it. I thought I'd just start with a little background on forecasting at Google and just how pervasive it is. My team does a lot of work in the kind of infrastructure planning space, but we actually also build the forecasting tools for use internally, and those are used across a wide range of application areas. So these are just some of the different metrics: volume, revenue, click-through rate, daily active users, retention, satisfaction, service levels that were involved in forecasting across many, if not all, of the different product areas within the company. And I like the summary note that one of my colleagues quoting him as, when there is a metric, there is a forecast. And that's, I think, very common at Google. We have so much data that we're swimming in and trying to predict and plan based on what the forecasts are telling us. A little bit of view into the specific application area that we're going to talk about in terms of data center capacity planning. Just to give you a sense of the scale, this is a photo of one of our data centers, which is, this one's in Belgium, picture on the left, and that's kind of one hallway that you see there. And this that's one of many around the world. This kind of gives this is actually our cloud infrastructure network that you see kind of globally. So we're planning capacity within each of these data centers down to a very granular level, understanding how that is, what the workloads by product area look like, what the workloads by compute cluster look like in each of the locations, kind of over time, and then also, looking at the flows between them, as you see here. There's another responsibility that we face at Google. So with that kind of as a little bit on the scale, I'll just kind of walk through our summary of what we'll talk about today. So we have automated many of the steps of design, generation, and monitoring of time series forecasting in an extensible and comprehensive framework. And that's kind of what our work has been around, to make it more scalable, to make it more accurate. So I'm not saying we have a system that generates forecasts with no human intervention, but I would say we build a set of tools that actually works quite well to assist us in forecasting and the processes related to forecasting. To generate and evaluate forecasts, we use nested cross-validation. Casey's going to talk in detail about the approach that we use for that. We run jobs in parallel using Google's computing infrastructure. And we'll talk a little bit about what we do internally, and then kind of point you in the direction of how you can build similar pipelines on our cloud platform. And we'll talk a little bit about the framework that we have for evaluating forecasts and the way we look at metrics. So that's roughly the summary of our talk. Again, really great to be with you. This is just the rough outline. Casey's going to give a little bit of background on the capacity planning problem from a conceptual level. Talk a little bit about the product and geographic hierarchy that we deal with, and in that problem space. Talk about the nested cross-validation approach, talk about the parallel processing approach, and then I'll say a little bit about the work that we do in metrics, and talk about where things are headed in terms of next steps with Google and with the tools that we have available for users as well. So with that, I'm going to turn it over to Casey.
Thank you, Chris. And talk a little bit about the capacity planning problem we face with data centers. Next slide is an example of a time series for a particular location. So we're trying to forecast demand for a compute resource over time. So in green, you've got the actual values for this location's demand, and we're trying to make forecasts into the future, typically at the lead time for ordering machine parts for this location. And if we're trying to meet a service level objective, maybe we're planning capacity up to the 95th percentile, which would be the top of the cone you see here at the end of this forecast horizon, which would be the lead time for the machine orders. So that's a little bit on how we use forecasts and in particular prediction intervals. Big focus here in this talk is how do we come up with good prediction intervals? And we're going to talk about how we use nested cross-validation to do that. We've got lots of time series and they're arranged in a hierarchy. One way we oftentimes cut this hierarchy is to think about the product areas first, and then the geographies that each of the product areas not only operate in, but really plan at. So some of the different product areas will plan at different geographical slices. So we've got the fleet at the top, and then we've got the different product areas like search and cloud and YouTube, the ones you're all familiar with. And say inside of cloud, you break it down by region, and then inside region, you can break it down by zone. So if you get a compute instance on GCP, you'll end up selecting what zone that virtual machine is in. And we need to make sure we plan capacity for that zone in a good way to satisfy your request and everybody else's. So nested cross-validation, I'd like to go through that idea a little bit and talk about how it's useful in generating prediction intervals. To evaluate our point forecasts as well as our prediction intervals, we're going to use a sequence of backtests, but we're not just going to use one sequence. We're going to use nested sequences of backtests. There'll be a second set of backtests inside each of the training sets that we have in an outer loop that is used for evaluation. So inside each of the outer loops backtests, we'll run another sequence of backtests and we'll collect up empirical errors. We'll fit a distribution to those errors. And because we're gonna try to generate a cone, there are gonna be lots of these prediction intervals, lots of these empirical error distributions, and we're gonna connect them up in some hopefully intelligent way to build out a cone. Tomorrow, Kashif Yusuf, who's on our team, is going to be talking in a Google research session about this very topic. So these are two sequences of backtests that are nested, and hence we call this nested cross-validation. Didn't make this term up. If you go and do a Google search, you'll find lots of resources on the term nested cross-validation or nested time series cross-validation. Okay, so let's say we take one data set. We'll just carve this thing up into multiple training sets. So we're going to start with an outer loop, which is an evaluation loop. We'll have many training sets expanding in size. and then there'll be a validation set that's of the length of our forecast horizon, and we're going to want to validate a model, evaluate a model to see if one model does better than, say, another model in this evaluation. But inside of each of the evaluations training sets, we're going to need to carve that up into smaller training sets, a sequence of them, and run an inner loop to generate the cones for each of the evaluation validation sets. So this is a little schematic on how these two loops nest. Next slide. So one of the great things is we get to reuse the inner loops in the work of the outer loop evaluation. So the time complexity here is linear, it's not quadratic. So we really just need to deal with all the series. So this is just one series depicted here, all the back tests. We're depicting multiple back tests here, and then we'll be doing this for multiple models. There are many dimensions to this problem. Just talk through those a little bit here on the next slide. Actually, no. Yes, here it is. So we've got thousands of time series in this product geographic hierarchy. We've got all these back tests. We oftentimes run daily back tests. We've got years worth of daily data, and we'll go back into the history and run upwards of a year and a half worth of back tests to evaluate multiple models. So back tests will consist of a start and end date for the training set and an end date for the forecast horizon. There's oftentimes an incumbent model that's being used in production to make forecasts and order machines. And our team and other teams contribute to the work of generating ideas for challenger models, and we'll want to test those challenger models against the incumbent. These three dimensions can be parallelized. We can parallelize 1, 2, or all three of these dimensions. Oftentimes we're able to do all three. Next slide. The tools we use to do this parallel work, it's Flume and Beam mainly, and Flume is Google infrastructure for running these large-scale MapReduce jobs. Thousands of workers, sometimes upwards of 10,000 workers can do the job in minutes that would have otherwise taken a few years ago or maybe a decade ago on a desktop in hours or days. We get a speed up of about 10x to 15x over serial implementations. And for those who are inspired in any way by what you see in this presentation, know that you can go to GCP and use the data flow product together with Apache Beam to run a very similar pipeline. So a bit of the roadmap here. There are 3 steps mainly in the inner loop that we need to take. We're going to take each triplet, a series, backtest, and model, and have the option to run each of those triplets in parallel. And that's what PPP stands for. Each of the triplets, or each of the elements in this triplet, will be run in parallel. That's what we can do with generating point forecasts, so we can carve up the hundreds of thousands of jobs we have that are described by these triplets and run each of them in parallel. The second step is reconciling the point forecasts. I label this NPP, meaning the series cannot be parallelized. They need to be held together, all the concurrent time series, so that we can reconcile them across the hierarchy. But the back tests for concurrent time series and the models for back tests over concurrent time series, both of those 2 dimensions can still be parallelized in the second step. The third step, we're fitting cones to the empirical error distributions. We're going to record those forecasting errors. We're going to take the reconciled point forecasting errors from the second step, record those errors, and then fit a distribution to the empirical error distributions. It's a great problem to have. You can parallelize most everything. The one little bottleneck here is the reconciliation, because you do need to bring together those concurrent time series into one worker. Next slide. Here's a little example on generating point forecasts. We're just going to look at 3 steps ahead, 1, 2, and 3 steps ahead. So maybe we've got multiple training sets, expanding training sets for the different back tests. This is all still in the inner loop for just one time series. We'd of course have many more back tests than just these 3, but we may be interested in a 3-step ahead forecast, as well as 1 and 2. We can generate this for all the time series in the hierarchy, and we're going to want to arrange the concurrent point forecasts so that we can have all the 1-step ahead forecasts and 2 and 3-step ahead forecasts from the same size training set across all of the hierarchy so that we can do the reconciliation. So this is just an example of 2 series that roll up into a total, which is the series on the right. Once we have those arranged, then we can go ahead and do the reconciliation. Might want to use something like the min-t algorithm, just a linear combination of the unreconciled forecast to come up with reconciled forecasts over the whole hierarchy. An important note here is that we do need to collect up in-sample fitted values to calculate the projection matrix. And this is a bit of a challenge when we think about extending this whole framework to some kind of ML model, but that's a topic for another day. Next slide. Okay, so we're going to record all the errors from each of the back tests for each of the series. And we might record additive errors, or we might record multiplicative errors, depending on whether we think the cone should get wider the higher the level of the series or not. We are going to take those reconciled point forecasting errors across all of the different back tests for a single step ahead. So for 1 step ahead, for series 1, we're going to have a collection of back test errors, and so on for 2 steps ahead and 3 steps ahead, and then across all the series in the hierarchy. And in this little 3 time series example with 3 steps ahead, it's going to yield 9 different histograms that we're going to want to take a look at and fit a distribution to, and then ultimately take the quantiles from those distributions and fit some kind of curve over them to generate a cone. Next slide. So here's an example of one time series and the 3 steps ahead, each of the error distributions. As you go out further in time, these error distributions are generally going to widen, and you can see the 90% prediction intervals on these 3 histograms, and they are indeed widening out. This is real data from one of our applications. And what we're going to want to do next is fit a cone to these quantiles. So if we're interested in the 90% prediction interval, we're going to fit these 2 lines in some kind of smooth way. It's not necessarily going to be smooth if you just connect up the points, the different quantiles, or sorry, the same quantile across the different steps ahead. Next slide. So again, a little bit of a plug for the research talks from Google folks, folks on our team tomorrow. Hao Yun is going to talk about generating better point forecasts using an ML model. Weijie Shen is going to talk about reconciliation, a new method for reconciliation, which we call min-k. It's a minimum Kullback-Leibler approach to reconciling point forecasts, and it's largely going to focus on intermittent demand problems. And then Kashif, like I mentioned, is going to talk about why we use empirical error distributions to fit our cones. These talks all relate to the steps in this inner loop that I've just described. Okay, so I want to go through this single time series example a little bit more so you can see visually what this looks like. As we take an entire history like the one you see here for a single time series, and then we're just going to step back in time and start our inner loop. So next slide. So the first iteration in the inner loop is to go back in that history and work with a smaller training set and make a forecast into the future and grab a forecast error. This will be a reconciled forecast, so we'll have to have the other series stopped at the same point. You make forecasts, you reconcile, you get the red line, you go observe what the actuals were, you subtract. That forecast error is then recorded, and we'll use that later to build out the prediction interval. So then if we look at another iteration in the inner loop further towards the end of the history, this is one in the middle, we record this forecast error, and then one near the end, we record up that last forecast error, and then finally, once we've got all those forecast errors recorded up, we've got this empirical error distribution, which is that histogram off to the right, and from it, we're building out the cone you see in gray. And we'll pick off that P95 from that cone, and that will help us set capacity for this location. So now the outer loop, and this is all just about the cone. So once you've run an inner loop, so you would have taken the green here and carved it up into smaller training sets, run that inner loop, collected up all those backtest errors, and built out the cone that you see here. And what we're going to record now is the whole cone and the actuals so that we can do some evaluation. How well did the point forecast do? How well did the cone do with respect to the actual blue that you see here? So this would be, say, the first iteration in the outer loop to do evaluation, and then we're going to step forward. This is one from the middle, and then we're going to step forward again. This is an example from the end of doing our evaluations. And I'm going to turn it back over to Chris, and he's going to talk about what we do with the information after it's stored. We run the inner loop that basically gives us for free most of the information we need for the outer loop. We store all of that and then calculate metrics from there that will enable us to compare models. So back to you, Chris.
Great, thanks, Casey. So I'll talk a little bit now about the tools that we've been building to kind of automate the evaluation of metrics for our forecasts. And I think the first point I would make is, you know, a lot of the automated approaches that we have are, you know, we're trying to optimize our models, and whether that's, you know, hyperparameter tuning or you know, automated model selection, all of that's done kind of on a single metric. And so, you know, when we kind of run in autopilot mode, you know, we're picking a metric and we're optimizing around that. But we found that actually when we want to diagnose and look at forecasts in more detail, we want a broader kind of assessment of that forecast performance. And so that's the area that I'm going to talk about a little bit more today, is kind of how we break things down and how we slice up the metrics about a forecast. And so we've come up with this kind of 5-category framework that has been helpful for us to kind of dissect the performance of our forecasting models from various angles. So the first category is accuracy. How closely models forecast adhere to the actual realizations. The second category is bias. I don't think I need to necessarily explain the detailed definitions here, but, you know, accuracy, bias slash calibration. So bias in the case of when we evaluate point forecasts, and calibration when we evaluate our prediction interval forecasts. So, and I'll talk a little bit more detail about each of these examples. Error variance, the spread of point forecasting errors around their mean. And I'm going to talk in a second again about how these relate. Accuracy risk, the variability in accuracy metric over multiple forecasts. And stability, the degree to which my forecasts remain unchanged over time. And, you know, sometimes I want a highly stable forecast, sometimes I want a highly adaptive forecast. And so we like to look at that as a metric as well. So we found that these 5 categories are a good starting point for us. And a couple of the merits of taking this approach, it does give us a more refined view of a model's performance than looking at a single metric. It enables trade-offs depending on business applications or needs. So we may actually look at these metrics and say, for our purposes, we're more focused on minimizing the bias rather than reducing accuracy. So we're going to, but now that we've seen the results, we're actually going to go back, re-optimize around a different metric than the one we had used before to really kind of focus on that aspect. So it enables us to make those trade-offs and maybe even go back and rerun our hyperparameter tuning, for example. The metrics can be computed in aggregate, so we can look at them kind of overall across forecasts. We can also look at them by segments or even for individual series, and really trying to slice and dice and kind of dig into what are the drivers of where we're performing well and where we're not. We assess them through back testing, just the way Casey described. You can see that last kind of outer loop where we're actually back testing both our point forecasts and our prediction intervals and gaining information back. We monitor them in real time. So let me do one example of kind of how these pieces interrelate, and then I'll show you a little bit more about the metrics framework. So this was a simulation that we put together, just a simple example to show kind of when we might want to look at one metric versus another, and how we how the pieces interrelate, how we dissect them. So I have 2 models here, Model A and Model B. And these histograms are supposed to represent the forecast errors that we obtain through backtesting. And so in the case of Model A, both Model A and Model B both actually have the same accuracy when measured in terms of mean squared error. So they both have a mean squared error of 9, but they're actually quite different. Model A is an unbiased forecast, but it has a high error variance. And Model B is a biased forecast, but it has a low error variance. So if I were, excuse me, if I were optimizing around accuracy, I might have trouble trading off between these. And if Model B was slightly more accurate than Model A, I might have picked Model B. But if I look at it, I may actually choose to instead, if it looks like that bias in Model B is correctable, meaning I can, essentially subtract 2 from the whatever's coming out of my forecast model, line it up back on that red line, and then have a lower variance model, then that may actually be what I want to do. So, excuse me. It's only through kind of dissecting at this level that I'm actually able to see, am I happy with the 9, or can I actually do better by changing my strategy a little bit in terms of what I optimize around? So that's an example. That's also kind of illustrates how these 3 categories allow us to see the various elements, whether it be the degree of bias or the spread. So the error variance is the spread in that distribution, obviously. So that's a little bit of the motivation behind the approach we've taken. Here's how we implemented it. We put together this kind of automated model selection evaluation report. So this is just the reporting structure that we're using now and kind of have built into our into this comprehensive framework that we're talking about. And there's a couple things that I like about it. So first of all, we allow ourselves to look at each of these categories, both in terms of the point forecast and in terms of the prediction intervals. For the prediction intervals, we don't look at the error variance. That's more of a point forecast specific metric. But we've essentially got, each row being one of the categories, and then we've selected one metric in each. We actually have the ability to swap in different metrics. So if I wanted a different accuracy metric, I could do that. With most of this stuff, we are defaulting to kind of volume weighted metrics. So we're trying to take a, weighting across multiple time series, multiple back tests. We're taking a volume weighting approach there. When we generate the metrics, we compare them to standard benchmarks. So I know, there's a lot of talk lately around, not just lately, but a lot of folks like the scaled error metrics we do too. We actually found that we like to see a little bit more specifically, what was the metric in the dimensions of the metric itself for our model, and then compare it, say, to ETS. So if I take that first example, now I see, okay, my weighted MAPE on model 1 was 0.076, which if I'm comparing it to the ETS benchmark, is a little bit worse. And so then we have the color coding that's kind of coming in there as well. So we take two standard metrics in this example. I had an ETS and an ARIMA model that was not a well-fitted ARIMA model, so that's why it kind of didn't fare very well. You see it's kind of red in that example there. But we compare to benchmarks, and then we can compare between models and actually do things like pairwise assessment, where we compare a couple models, decide which one was the winner, and we do that with a significance test using this Diebold-Mariano test for predictive accuracy to make sure that when we've called a model the winner against a different metric, we have confidence that it is. And you'll see, this is actually quite typical. It's not the case that one model is going to win on every metric, and so that's then when it comes back to these trade-offs that we have to kind of assess. And so anyway, a little introduction to just a sneak peek into what we use internally as a little diagnostic framework. We can run that thing actually in a more detailed way. So if we want to have multiple accuracy metrics, multiple bias metrics, multiple kind of metrics in each category, we can do that. You'll see in the prediction interval section, for example, we've taken pinball losses. So I apologize, there's a ton of acronyms here that if folks have questions what some of the acronyms were, feel free to give me an email or ask at the end. But in the accuracy section on prediction rules, we've got pinball losses, weighted mean percentage pinball losses at different quantiles. So we're able to assess across different quantiles. Then we have a CRPS-based metric because in our capacity planning work, we tend to focus on the upper quantiles of the error distribution. So we then take what we've kind of created this metric called weighted mean upper CRPS. That is looking at the upper quantiles, kind of the upper tail only, and then doing a continuous rank probability score across those upper pinballs. So that's a little bit more detail. We don't always go to the more detailed report. Sometimes we get enough information just by looking at the base report. And as you saw in the base report, if I go back here for a second, we were looking at the P90, which was may have likely been in this example the quantile of most interest out of that set. And so then here we pulled in a few extra. I may or may not need that level of detail, but we have it available. And I think this is an old version of this picture. I think we probably have twice as many of these in our library now that we're able to reference. So that's a little bit on the evaluation use of metrics, but there's actually other angles to the metrics as well. So that I can look at metrics over time. These bottom pictures kind of show over a series of, I think we ran backtests every day in this example. These pictures on the bottom, so over close to half a year's worth of backtests. How did the metrics play out for between two models over time? And so I can look at any model, see if it's getting worse. I can compare two models, see how they do over different points in time. This would be obviously across a set of time series that I'm looking at. And then we can put in things like tolerance bands, where we'll actually then alert ourselves, okay, if this performance monitoring that I have going over time, if it exceeds that band at a certain point in time, that's when I'm going to get a triggered alert on it. And so I'm not constantly having to check this stuff every day, but when things get out of whack, the system then can tell us that it's out of whack, and we go look at it, figure out if that's something that we can adjust in the model, or if there's a true increase in variability in the system, or if there's a data problem. Right? Those are commonly the drivers of crossing those types of thresholds. We also look at different windowing or tracking windows. So I've shown this example here where on the top, where we might look at the past 3 months, the past 6 months, and the past year, and measure various metrics. So then I can see, am I doing better more recently compared to how I've done over the full year? So am I trending up, trending down? We played around with, should I do past 3 months versus the 3 months before that, et cetera. So, we've kind of played with different methods of this. This view starting to, seems to be working okay. But, none of this work is a finished product, and it's kind of it's an ever enhancing piece of art that we work on together. So that's a little bit where our thoughts have been at lately in terms of tracking that. And I think a lot of folks run into the challenge of there's so many ways to slice and dice this information that if you don't start putting a stake in the ground in terms of these are the metrics that I'm actually going to look at, this is the way I'm going to look at it, then you're swimming in soup, you're overwhelmed, and you don't know where to begin. So that's been also kind of where we started with, I'm going to come up with 5 categories, I'm going to look at those categories, I'm going to track it over time, I'm going to slice it this way, just to move the ball forward. And I remember when I came in, if I think back kind of a couple of years ago when I started, shortly after I started at Google and we started working on some of these problems, we would have debates over, how to compare 2 models. And now we've kind of settled that debate by having a much more of a defined approach and taxonomy for how we're going to make comparisons. I talked about how we compare over time. We also compare models and assess metrics across forecast horizons. So if I think about a forecast that goes out, we make forecasts out anywhere from a couple days to years. And when I make forecasts over a time horizon, I may have a model that does really well on short horizons, but really poorly on long horizons. And it may turn out that the horizon that I'm most interested in terms of driving my cost or my financial impacts for my decision is some long horizon. So if that's the case, then I want to see how my model performs kind of by horizon. So we take this approach where we've actually computed the metrics at every horizon, over, I think these examples are over maybe a 6-month horizon. We were comparing 3 models. We had one that was the clear winner, and I kind of just wrote out some of the sample dialogue that you might see where, the annotation would be forecast B's short horizon weighted MAPE. It's consistent with forecast A, but it offers superior accuracy at longer horizons. And it does it with considerably less bias. So that's the picture on the right. This was actually a real example that we dealt with. And again, we had to pick 2 metrics to look at. And we chose weighted MAPE for the accuracy side and then weighted mean percent error on the bias side. Again, this is where with 30 or more metrics to choose from, you're swimming in the soup if you're not kind of specific about how you're going to look at it. And this is a little bit of the approach we took here. And then lastly, we're looking at our metrics across hierarchical levels as well. So, I've got the same columns that I had in a previous slide. I've got different tracking windows that I'm looking at, but now I'm actually, taking, for example, a top level series, accuracy metrics, bias metrics, coverage metrics, pinball loss metrics, looking at the top level series, intermediate levels, and then the bottom level series. And that's quite helpful for us as well, because each of these levels may actually drive a different use case. Those bottom level series are what tends to be where the rubber hits the road in terms of making decisions about where I'm going to put compute infrastructure. But those top level series drive a lot of financial planning. They drive a lot of kind of long range planning decisions, and those may be also the forecasts, those aggregated forecasts may be what drive my parts procurement, for example, as well. So important to look at it across the levels. So that's a little bit on the framework that we put together. Kind of tying it back, we had the process that Casey walked through for how we generate forecasts. This was kind of the metrics piece. And I had one, I thought it was my last slide. I had one more point here on, we also look at economic impacts. So, we will measure these, we assess these metrics both, in terms of the pure forecasting dimension or that we look at, but then we may also go out and cost them. And so, we kind of have this stock out and inventory cost of the XX percentile, or what I'm starting to call it the pinball cost, that we can actually measure. And then we can dissect that into both the inventory cost side and the stock out cost side, and start to quantify the benefit of an improvement in accuracy, for example. So that's a question that we commonly get is, what's the value to Google or to this business if we improve our accuracy by 5% or 2% or something? And by having these quantifications, we're able to, go beyond just, well, I've improved my mate by 3% to this is going to save X dollars for business by having that quantification. So that's actually also built into the tooling that we put together in this framework. So that's the kind of the technical side. A couple of notes on where we're headed, and then I'll stop and open it up for questions. I called this the infrastructure and models of yesterday, today, and tomorrow. So the left side is kind of where we've been, kind of where I think where we are is a little bit in between these two, left and right is what I'm trying to say. But the left side is kind of where we're going from, and the right side is where we're going to. Going from being more based on classical time series models, and going to being that we're increasing our reliance on machine learning models, where they fit in, where they help us be smarter. We want to drive that, invest that, adopt that. And as we go through that journey, it actually changes some of the tools that we're using. So Casey just talked about, we're doing in Borg and Flume with the data flow product on Google Cloud Platform. That's working really well for us now. I can envision a future where we're running more on our TensorFlow TFX pipeline, for example, and that would be code in TensorFlow as opposed to the Python and C++ that we use today. On the reconciliation side, Casey's walked through the machinery a little bit of how we do reconciliation in a post-process basis. We're doing research now on how we do it within the process, or peri-process reconciliation, where we're actually making that part of a integrated component of the machine learning model to output reconciled forecasts directly, rather than having to take the output of a model and then go generate the reconciliation separately. Same thing with the prediction intervals. Today we do it empirically and post-process, and please come to Kashif's talk if you want to hear more about the motivation for why we've taken that approach. And in the future, we may generate those prediction intervals again as part of a machine learning model. So this transition is driving the transition in terms of the technology and the approaches and the research that we're taking in our team. We do see time series as a huge driver, huge value potential for the company. So this was from I think 2018 McKinsey Global Institute report that came out on the value potential of AI, and they had time series data type as the second highest impact, and those so those ranges are the percent of total value potential coming from that particular data type. So I mean, I would say this resonated with us in terms of the importance of time series. That's why we invested a lot in the area. Talk a little bit about some of the tools that we have available. I did want to highlight on that, give a shout out to the work that's being done really on the customer facing side of Google. We've got a set of open source tools, TensorFlow Probability, being one of them. And if you came to our talk or saw our talk last year in Greece, I had Nicholas talk a little bit about the TensorFlow probability product and the Bayesian structural time series that's built into that. So that's one of the tools that's out there, and I've got some links on the bottom of the slides. We'll make sure that these are available for folks who have these links. TensorFlow, so TensorFlow probability is a specific time series and probability modeling, Bayesian modeling framework within the general TensorFlow. We also have a research direction around temporal fusion transformers, and that's also going to be one of our talks tomorrow. So I want to reiterate Casey's plug. Please come and see Sir John's talk on TFT forecasting, temporal fusion transformer forecasting, and CubeFlow being the last one. And I won't say more about that because that's not an area that I'm an expert in. That's one set of tools on the open source side. We also have BigQuery ARIMA, which we're now offering through Cloud BigQuery. The idea is that you can now write your basic forecasting model calls directly into SQL and directly into SQL that runs on BigQuery. And BigQuery is so scalable and fast. Casey was telling me he was running very, very large data sets very quickly using these tools. There's a sample of a kind of SQL call where we're running an ARIMA model directly embedded into the SQL without a lot of without a lot of code overhead, without having to swap to a different platform. So it's a reliable forecast with a few lines of code and little to no pipeline engineering. I think that sums it up well. It's got automatic cleaning adjustments, one of the capabilities that we built internally and have embedded into that product. Holiday effect adjustments, we have a holiday database that's built in. STL decomposition, double exponential smoothing, ETS for the forecasting, as well as ARIMA and auto ARIMA forecast types as well. Two more, and then I'm getting very close to the end here. The AutoML tables is another component of our offering. So if I think about the BigQuery is built upon BigQuery, and then we have AutoML tables is a separate offering that's tied in with our AutoML offering. I put a link there as well, cloud.google.com/AutoML-tables. And lastly, there's work done in the cloud solutions area, and this was actually the team that Nicholas, if you remember his talk again from last year, this is the stuff that his team has worked on a little bit, is the demand AI tool, and that is a retail-focused forecasting tool that we started sharing and talking about with the public, I think at Cloud Next most recently a few months ago. So that's kind of hot off the press, and I think for the folks in the retail space could be a very exciting area to learn more about. So I put a link there as well. Lastly, a plug for some of our talks again tomorrow. So these, as mentioned, these are the 4 talks that we're giving. Is tomorrow at 4 Greenwich Mean Time. Welcome you to come. And just a quick shout out to our team. This is a photo of my team back in Sunnyvale, California. This photo was taken in January, just to, we're one of many forecasting focus groups at Google. We've talked about some of the work that our team does. There are other groups at Google as well. But especially when everybody's remote, I think it's nice to just remind ourselves of, it's really a human process, individuals contributing to this work. And so my thanks to all the great contributors that have made what we've done at Google possible. So I'll stop there. This is how to get in touch with either of us if you need to, and hope that leaves enough time, George, and Nikos for questions.
Thank you very much for an excellent presentation. I found it very interesting myself. And although I already have a question, I prefer to give first space to the audience. So please feel free to ask your questions. I can read the questions from the chat and then either of you can answer them. Do you ever run into multiple testing bias by evaluating too many forecasting models or too many tolerance bands? If so, how do you prevent over-managing this?
Casey, do you want to take a cut at that?
Yeah, sure. We do try to correct for multiple comparisons when we run our statistical tests. When we have 4 models in the mix, there are lots of pairwise tests, and we make a correction at the end to the Diebold-Mariano the test statistic and the p-value that comes out of that test. Yeah, it does tend to increase these p-values, and it becomes harder to say who the winner is. And then that just means we need to work harder at the leading model to see if we can improve it, get its bias out, maybe reduce its variance in some way, or see if we can get a clear winner. So yeah, that's definitely a challenge.
I have another question here. It's about how people can get the papers. I guess this will be coming up in tomorrow's talks.
Yeah, unfortunately, for 3 of the talks, we don't have papers. For 1 of them, we do. The temporal fusion transformers talk, Surgeon does have a paper out there and a GitHub repository where you can get all the code. The other 3 talks, we're still working on the papers. They'll be coming out at some point.
Yes, stay tuned. Definitely, you know, this is work that we want to get out and documented, maybe in IJF or somewhere else. So stay tuned.
Looking forward to that. I have another question here. Why did you decide to use empirical prediction intervals instead of directly fitting models with additional pinball losses?
You'll see in the ML talk tomorrow that with a quick change to the loss function, we can do exactly that last thing you suggested. But the main reason we use empirical error distributions when we work with classical time series forecasting models is that we find those models don't have very good intervals. They don't oftentimes have the right coverage, and they're not as accurate as the intervals we can generate using empirical error distributions. We do have hope for the ML approach, so we'll see in the next few months whether we can get some improvements over our empirical error distribution approach. If you want to hear more about some of the studies we've done internally to prove this out or prove it to ourselves that these empirical error distributions are a sensible way to go, come to Kashif's talk tomorrow. He'll be talking all about that, and we'll give some additional detail on why this method seems to work.
Yeah, and I think just to add some color there, you know, when the actual errors fit the model distribution, then you know the error distribution that's assumed in the model, then we have then using what's available directly from the model-based interval makes sense. But you know, what Kashif's going to show is, especially when those empirical errors don't look normal or don't fit the assumption that's in the model, then you know that we've got a lot more flexibility in fitting to the reality that we see. So more tomorrow.
Just to make a note that Skander has pasted some links to who are interested about resources. Another question I have here is, can you characterize the types of users who are attracted to your advanced methods? I guess apart from internal consumption, that is.
Nikos, could you repeat that?
Can you characterize the types of users who are attracted to your advanced methods, machine learning, etc.?
You meaning inside the company or outside the company?
I would imagine more for the outside, for the tools that Chris presented in his last slides, I would imagine, but internal as well, if that's relevant.
Chris, do you have any information on that?
Yeah, we've had a lot of leading companies interested in and you know actually alpha testing some of these capabilities, beta testing some of these capabilities. I'm not sure I could summarize up exactly what, are there any differentiating characteristics, but, I think the tools are, that's why I also think we have this range of tools where you've got the BigQuery ARIMA is a nice, easy to use, quick tool. It's not super advanced. It's highly intuitive. And then we've got the more advanced tools that are, pure kind of ML based and, or retail specific. And so depending on your application area, you may gravitate toward one or the other. But if you're interested in learning more, let me know. I'm happy to put you in touch with the folks that know more about these areas. That Google's such a big company that I can't speak to it as well as others.
I have two more questions here. One of them is about the forecasting facilities within your SQL code in BigQuery. Are you using Python to do the computations or something else?
I believe that's C++. It's some of the same code base our team is using to run ARIMA and ETS models. Okay.
And one last question before I pass to George. Has COVID presented challenges for forecastability? Are you having to reassess or retest your models?
Absolutely. And I would actually say it's kind of a two-sided story for us. So the other thing that, so absolutely it's kind of thrown things off, and it's a completely kind of unpredicted event and had huge impacts on our business. Where I think our models have actually been super helpful has been in counterfactual forecasting. So we've been able to, look at, hey, what was the forecast back in February 2020 or March 2020, right before the impact started, and what was the range of uncertainty there? And that gives us a very clear kind of retrospective on how much did the reality actually diverge from what we would have expected, right? And because we have, we have good forecasts and good prediction intervals, we're able to say, in what cases did we break through the, 90% confidence interval of what we thought would be normal, which unfortunately, for all of us, I'm sure was the answer was pretty often, but not necessarily everywhere. So that's how I would say it's affected us in both those ways.
I think we're running out of time for more questions. So let me thank you first before I pass to George. Thanks again for your talk.
Pleasure.
Thank you.
Thank you both Casey and Chris for a fascinating talk. I really enjoyed that. And also just to take a step further and thank Chris for all the support to the ISF and Google in general. A great practitioner to have on board, and I hope you're enjoying the ISF, and I hope you keep on enjoying it for the rest, for the next few years. So cheers. Thank you for all your support.
It's been a pleasure. Thank you for having us. Take care.
Thanks again. Take care.
Thank you.